Welcome to the next webinar in GoProto's Office Hours series. Today we'll be talking about 3D Elastoprint with TPA elastomer, what, how, and why. You'll notice that your questions are on the slides as we go through, but feel free to submit your questions in the Q&A. You also, if you see a question over there that you like, you can also upvote that, and we'll try to get to it as we go. We'll also have some additional time at the end for additional questions. All right, so to get started, we have Jesse Lee. He's the president at GoProto. Jesse Lee is a 25-year student of the rapid manufacturing space. He's been a part of incredibly diverse program development or product development programs, from early prototyping for products like the iMac in the 90s through high volume additive manufacturing for projects like HP's 580 color printer. Listening to client partner needs, utilizing the latest and greatest array of manufacturing technologies, and working with the best people in the product development and manufacturing community is what Jesse finds most exciting. We also today have Rebecca Fecto from Evonik. She's a business development manager in Evonik's high performance polymer business, focusing on additive manufacturing by supporting material integration into hardware manufacturers and end users. She holds a BS in chemistry from the University of Pittsburgh and has been with Evonik for 3 years. With that said, I'm going, let's see, we're going to move on to the agenda. So this is what we're going to cover today. It's going to be specifically on elastomers for flexible applications. We're going to do a really brief introduction on GoProto, and then followed by a very brief introduction on Evonik. And then we want to really get into the meat of it with an introduction to multi-jet fusion, because this is specifically the technology that we're talking about today. And then onto the 3D Elastoprint. What is it? Why do we use it? What are the material properties, part properties? And we'll go through several different reference designs and examples of potential applications. So to start things off, we are going to go into who is GoProto. So Jesse, do you want to do a brief introduction?
I do, yes. Thank you very much, Kristen, and thank you everyone for attending. I'm excited to talk to you today about this new material. Just as kind of a little bit of time reference, this material was introduced as a commercial product at the end of October. So it's a very new material for the process multi-jet fusion, which is also only about a 4-year-old technology in the market. So it's a new tool that you have to accomplish old problems and new problems that have been challenging us on the elastomer space. So hopefully you find today's presentation useful. Again, thank you for joining. So then just a quick summary of GoProto. We're a rapid manufacturing company. We're what you'd call fulfillment. So we do everything from early concept model design prototypes up through production, higher volume parts in traditional manufacturing. So we use a combination of 3D printing or additive technologies, and then cast urethane, as you'll see there. Machining is a very important process for us. We do a lot of machining, so we understand subtractive as well as additive. It's very important to know. And then we do injection mold tooling and parts molding. So a big part of our business is that industry. So we're often looking at what is the balance between 3D printing and versus injection mold tooling and molding of parts. So that's important to know that we can come and look at this objectively. We'll talk about that a little bit more later. We also do sheet metal in both prototype through production volumes. So we're very interested in doing 1Z, 2Z, 5, 10, 20, 50 kinds of quantities for sheet metal in steels and aluminums and so on. So when you think about your bill of materials and all of the mechanical parts that are on it, you're often going to have a rigid part, a sheet metal part, and then potentially elastomer, which is what we're talking about today. So it's important to know that we can do that part of it as well. And then additive manufacturing is important to know that we spend a lot of time, and that is essentially using 3D printing to make production parts in higher quantities. So it's really the same technology. It's just making more of it, maybe doing a little bit more analysis up front in design for manufacturability, and then process control, and then inspection and packaging and so on in the end. So some slightly different workflows that make 3D printing into what is known as additive manufacturing. We're hearing that term more and more in the space now. And then, of course, finishing. So we concentrate, yes, we can make great parts, but we need to have graphics, we need to have inserts, need to have colors and textures and so on. We very much focus on finishing to put the final touches on your parts to make them usable. So again, just prototype through production, quick, on turn or on demand. Custom manufacturing is GoProto's business model. Yeah. The next slide, I believe, is...
Great.
Yeah.
So next we're going to move on to Evonik. What's their role in all of this?
Since we are a B2B company, I like to start with who we are and why are we involved in this conversation, because a lot of us don't know our name. So basically, we are a chemical company, a specialty chemical company. Scope and scale, we're about 15 billion US dollars annually, operating in over 100 countries and have over 32,000 employees. We have 4 different segments we work out of. So from specialty additives, where a small additive can have a big impact on a formulation. We have nutrition and care, where we're concentrating on items to support or materials to support animal and human care. We have performance materials, where we have just classical chemistries that we try and optimize performance. And where I come from, smart materials, where we have not only additive, but other structural foams, lightweighting. We're really trying to lead beyond chemistry, and we work toward this common purpose of improving life and now in the future. The part of this smart materials that I'm in, many people aren't aware that we actually are the world leader in development and manufacturing of customized polymer materials and additives for 3D printing. We've been in it for over 20 years, and we've been setting these quality standards behind the scenes. And this is such an exciting project and an exciting launch, because it's the first time that we've really worked with an end user as well as the printer manufacturer, being HP. GoProto is just really essential to getting this material to market in the right way and understanding that there's really a need for it. So yeah, just to add that in, that's why we're here. That's why I'm here today, to really support GoProto on what he needs on the chemistry side.
Thank you, Rebecca.
Great, thanks, Rebecca. So next we're going to move on to multi-jet fusion. We want to give you just a brief introduction so you have some background information on what we're talking about.
Excellent.
Jesse, you want to go ahead?
I do, yeah. So again, talking about multi-jet fusion or 3D printing and GoProto, multi-jet fusion came on the market in about April, May, June, in that ballpark of 2017. So it's fairly new powder bed technology. So what happens is layers of powder are laid out. Fusing and detailing agents are jetted onto the surface of the powder in the cross-sectional shape of the part, and then a high-intensity energy source is passed over, and wherever the droplets have been applied, the powdered material sinters together, and then that process repeats layer by layer, and you build up your part. It's important to know that there are no supports in this process. It is a powder bed technology, so the areas that are not fused, so that are not part of the part, remain unfused, and they are surrounding the part to support it as it's built. So unlike other processes like stereolithography or digital light processing, or say additive powdered metal that have supports that we have to mechanically remove afterward, this process results in parts that don't have supports. They just have powder that needs to be removed. So it's important to know that, because that affects some of the questions you all had of geometry, design constraints, and so on that we've kind of got listed here. So these are, in the background there, we've got pictures of the printers. These are at our factory in San Diego. We've got 6 of the 4210 machines and 2 of the 5210s, which are the newer versions. The TPA material runs on the machine that is in the printer part of the machine that is pictured here in the background, the 4210 machines. So then some things about this process. Why did we decide to jump into the HP technology heavily? And one of them is working closely with HP to master the technical side of printing parts on these. HP is an extremely highly customer service oriented company. It's been great to work with. They've helped us partner together to make the best parts we can, make this process as best we can. And then they introduce and facilitate the great conversations like we have with Evonik to come up with new materials and new ways to solve our customer needs. There has not been a great solution for elastomer 3D printed parts in the market to date. There's been essentially fused deposition modeling, or FDM, that has had a TPU material. There was a material in selective laser sintering that was an elastomer that was okay, but kind of crumbly and didn't perform well in terms of isotropic properties. And there's been some DLP technologies, as well as, like, say, Objet, that those materials are photopolymer approximations of elastomer. And they leave some things to be desired. So we've jumped into multi-jet fusion aggressively with the nylon materials, glass-filled nylon, PA11, and now the TPA has come along. Or TPU and TPA have both come along. We've researched them carefully. We've really worked hard on TPA and introducing this material because we know that it has properties that solve a lot of what the market needs and what you all as users have said you need and as customers. So then why this process? Are parts isotropic? That just means, do they perform the same in X and Y direction, the horizontal plane, as well as the vertical plane, or the Z, the build direction? Most 3D printing processes really suffer in strength and material properties in the Z direction because you end up having layers that are stacked on top of one another that don't often fuse completely between them. So the part will fail potentially if in the Z direction, not necessarily because the material fails, but because the process of layering kind of creates a weaker bonds in the Z direction. So an exciting thing about HP is you get complete fusing between those layers. So they are much more what's called isotropic. They will perform the same or very similar in the Z as they do in the X and Y in most properties. So that's a very important thing to be able to use this process for production. So that's an important property to be able to talk about. Excuse me. What's the largest part size? The build size for multi-jet fusion is 11.2 inches by 14.2 inches in the X and Y. So 11.2 by 14.2 by 11.2 tall. So fairly large parts, not as big as some of the other technologies like FDM. SLS can make larger parts. So building in sections and being able to fabricate together if they get bigger than that is important. And the TPA is bondable. It is something that we can print in sections and fabricate together. What are the design constraints? Again, these are questions, as Kristen mentioned earlier, that you all some of you had as you registered. So these are directly from the market. Design constraints, that's an exciting thing about 3D printing. Why 3D printing is interesting because you don't need tooling to make parts. You don't need to do things like draft and consistent wall thickness like you're used to designing for injection molding. Undercuts only become important in that we need to be able to remove the powder. It needs to be something that we can get compressed air or tumbling in to get the powder out. But you can make parts, I'm probably little in your screen, but you can make parts that are incredibly complex, lattices and so on, that you can't make with any other process than additive. So it unlocks the design freedom of additive, and then you have a material that is actually usable and is going to perform like a production elastomer. There certainly are design constraints, and that's important to know, and we can talk with you about your individual products to go through it. But there are things like sort of minimum wall thickness. You don't want to get features or walls that are less than about a millimeter. You start to get below a millimeter or 40 thousandths, and things start to become wishy-washy. Sometimes they'll work great, sometimes they won't. Depends on your particular design. Making real thick parts can create some thermal load on the printer, so you can get things like elephant skin, it's called, where you get some surface imperfections and sometimes hard to hold tolerances and so on. So yes, there are definitely things to consider. We'll go through some of those as we look at some examples of parts later, some applications. And then, are the parts production ready? That is something that's really important to understand. That's why we're so excited about this, is because this printer, the multi-jet fusion process, one of the main reasons we're interested in is because it's fast and can produce a lot of parts well. It's powder bed technology, so parts can be stacked together or nested together, kind of like a game of Tetris, where we can fit a lot of parts in that cubic volume and then be printing. We have 8 printers, so we can be printing a lot of parts every day. So we can make thousands of parts. We've done, for example, a lot of PPE parts like headbands for face shields, and we produced thousands and thousands of them. You've probably seen stories on LinkedIn and so on. And now to be able to do that same kind of volume in an elastomer part that is production grade. This material, as Rebecca will talk about in a little bit, it can be made in lots of different forms, including a powder technology or a powder so that we can print it. It then can make very similar technology or very similar chemistry in the injection molded version. So we could go through into the injection molding side. So it is a production ready process in a production ready material. And that's very exciting. It's also very repeatable. Everyone wants parts in volume to be the same part after part, and that's what this offers. Are multi-material parts possible? That's something important to address. Several of you talked about. We all know, it's very interesting to think about overmolding and co-molding. At this point, it is a single material print process. The HP technology in general, it adds droplets to the surface of the material and to do the fusing and detailing on the sides to make sure that there's no thermal bleed. the concept is that with different pixels, just like with color printing, you can do different properties, and that will come at some point in the future. But for now, we're still kind of in the, call it the Model A version, where it is a single material at this point.
But Jesse, one question that just came in that I think is relevant here in terms of design consideration and multi-material is, can you get a dual durometer TPA in one build?
Great question. Same at this point, it is a single durometer, and it is 90. But something that's really important is that we're all used to thinking of durometer in terms of how far your thumbnail will push into it, how soft it feels, and that usually is in an injection molded part that has a solid wall, because that's how we've been able to produce it. But sometimes when we want parts thinner or more cushy, maybe we'll go to foam. Like Rebecca said, that the TPA is available in a foamed version. So you can kind of introduce air essentially to create pockets that make it feel softer. Well, with 3D printing, you can vary again, I'll hold up this little part. You can vary the lattice, you can vary the density of the part to get the cushion that you're looking for. So, and you can vary it over a part. So that starts to really open up design ideas. So one of the applications we'll be talking about a little bit is footwear, for example. And say, you know, so you've made a heel for a shoe. I think my screen is showing larger, so I can show this later. You've made a heel for a shoe, and you can kind of see it in the camera. Where you're standing, you're going to want the most support because that's where the weight is generally. But out toward the edges, you're going to want a little less so that it's lighter and so that you can get some kind of different dynamics as you step, you know, at different angles and so on. You can vary the durometer by varying the amount of density so that you can get different cushions. So it is right now one material, one durometer, but through design considerations, latticing, lightweighting, and so on, we can help you with that. We offer that service. We can get you different cushioning, you know, that affects the same thing as durometer.
Yeah. And Jesse, if I can just make a comment.
Of course.
So when we were early in the project and talking to a lot of big athletic footwear brands, and I showed them different lattices, a particular partner, and it was the kind of like the lattice that you had, and I had a thicker one and a thinner one, and I had a few other parts, and they said, "Oh wow, this is amazing. Can we get one of these, and one of these material?" And I said, "It's all the same material." And he was really shocked, like, "What? This is all the same material? You mean you can put that in one part?" So yeah, just to emphasize, you really have to think about it differently because some of the design constraints are gone with that particular portion, where you can really vary wall thickness, density to get that it feels like it's a different durometer depending on your part.
That's super well said. Thank you, Rebecca. Also, Kristen, I'm showing three lattices here, 3 cubes. You can vary the shape within the part. Like these are 3 different little cubes that have different shapes so that you can get different performance out of it. And again, if you're looking for, often we're with elastomer parts, we'll drop them, they're bouncing everywhere. With elastomer parts, you're looking for the Goldilocks softness, the Goldilocks performance, right? It needs to feel just right. It needs to give enough to be able to say allow assembly, but be rigid enough that it holds its shape and so on. And often that can be achieved by different shapes. And you may incorporate different shapes in your single part. The cool thing with 3D printing is that you could send us, like, these are 3 different versions. You could send me 50 different versions. We could put it all in one print it, and then you try it all and we have it back to you in a week. And so you can quickly get through finding that Goldilocks. That's often a big time suck, is just that. And also you just kind of realize that with different shapes, you can get the performance you want, so you can quickly get beyond that and not be so hung up on that part of the design. Instead, just, you know, move on quickly because it's more natural to the type of design you're trying to make. So getting through that quickly is a huge advantage that 3D printing and additive in this material brings. Awesome. Okay, so then here's this is kind of similar, but this is a different slide. Some of the things that this process offers is fast, efficient, and cost-effective, kind of like I just talked about, actually getting through design iterations quickly, finding the right design, and knowing that you have a material that is production capable, so you're not having to make a compromise for what is like a 3D printed photopolymer version of elastomer that kind of feels bad, and you're like, well, it's not going to feel just like this in production. You don't have to make that that excuse to your designs as much anymore. You know, this is something that is much more production capable. So that's going to help speed. Then the parts themselves produce very quickly. We can produce parts in 2 to 3 days. It's very efficient. Powder removal is quick and easy. It can be automated. We tumble it so your cost is low, lead time is fast, and they're consistent. And then, you know, we talked about cost effective, being able to nest together well. A big discussion around 3D printing and this process in general is when we were talking about design considerations, it's important to be thinking about nesting. You know, how are these things going to fit together is important. That's something that usually isn't thought about with injection molding. But if you say take apart and are clever with the way that things can be nested together, then we can incorporate more parts per build. You may say have a boss that you want to have that uses it or that you use to attach it to another part. Instead of printing it standing up, you can actually print it with a living hinge in it, folded over so that your Z height is way smaller. And now instead of printing only 5 per build, we can print 10. You know, that kind of little trick can make a massive improvement in your cost. Production grade material, we've talked about this. The whole point of this webinar today is talking about this production grade material that's available now. It's very repeatable. I mentioned that just briefly a second ago. That's important. When you have a production process or even a prototype process that you want to go to time and again, you want to know that it's repeatable, that you can count on the same results coming out of the process each time so that you can truly work on your design rather than having to make considerations for a material or a process that varies. Great part cosmetics. We'll talk about finishing. That was one of the processes that we talked about. GoProto has come to this this whole technology in general, knowing that we're not going to be able to just make, you know, gray parts, which right now the material unfinished. Kristen, if you wouldn't mind, this is an orthotic shoe part that is just a tumbled finish. It's gray, kind of matte, even gray finish, and that works for some non-cosmetic applications like this. If it's going to be in a shoe, doesn't really matter as much. But we in San Diego, I've got 2 parts here that are ducks that we'll show again later. One part is just the tumbled finish, and then the other one is vapor smooth. So this process, this material, vapor smooths. We have a machine in San Diego that exposes the parts to a vapor solvent, and it slightly reorders the material on the surface and makes it look much better. It's just darker, nicer, consistent, even production grade finish. It also improves the mechanical properties of the part. It improves the elongation. We'll talk about that a little bit more later as well. Thank you, Kristen. All right, and then I think strong isotropic properties. We talked about that. This material performs. I mean, here are these parts in compression. I can put them this direction, rotate them. I'm small in your screen right now, but isotropic properties in compression as well as in elongation are very similar in X and Y, as well as Z. Okay, so then moving on to, you know, questions around, and part of our business model is to be able to help you with the blurry line of product development and manufacturing. And this slide shows the study we've kind of shown of generally where the processes fit as you increase your volume in the axis on the left versus the stage of your process along the horizontal axis. Ideation and prototyping early on, additive manufacturing is a great fit right there. That's in the blue, if you can see, and then and then the green section, there's an overlap between the injection molding and additive manufacturing. So in, you know, less than about 50,000 parts or so. Also considering your part size. If your part size is large, this equation is going to change. There's lots of other considerations that can change where this graph lies. But in general, less than 50,000 or so, 3D printing or additive manufacturing might be a good consideration. Gets beyond there, no question, injection molding is still going to be more cost effective. So you need to be thinking about, if you're doing mass production, 3D printing is still a cost, I wouldn't say prohibitive necessarily, but it's definitely a higher cost. So we often get to a point where we'll quote both and talk about maybe your design considerations, because as soon as you enter in other considerations like design, maybe you're going to be doing mass customization, like you want the same basic design, but you're going to be tweaking each one slightly to meet a customer need. If you're going to be changing your design often, then and you would have to make tooling modifications for injection molding, then this calculation will change. But in general, we would like to show that as you kind of go up into 50,000 or so, and in your stage along the horizontal axis, you'll see where the processes fit, and we can help you kind of go through that analysis.
All right, moving on to the 3D Elastoprint and the TPA elastomer itself. So I believe, Rebecca, were you going to discuss the TPA?
Yeah. Just to explain a little bit more about the chemistry, it's a thermoplastic. It's part of the TPE, thermoplastic elastomer family. It is TPA, thermoplastic amide. So what it is this particular version, a block copolymer consisting of hard segments and soft segments. The hard segments are polyamide. It can be a polyamide. This one is based on PA12, as we are the market leader in producing PA12 back to the butadiene. So we have a lot of formulation capabilities as we're producing the material. The PA12 gives you high chemical resistance, high abrasion resistance, and the polyether soft block gives you high impact strength at cold temperatures and gives you the flexibility. So this material, and we'll talk about it a little more, it's really known for its low density, meaning it's very lightweight, high energy return, high elasticity, and a broad processing window. Not just for 3D printing, but also in injection molding, it's known for having a broad processing window. Traditionally, the chemistry can be molded, extruded, foamed, and we use it in applications like foam for midsoles, for high-end sports shoes. It's used in football cleat plates. Tubing for automotive and medical catheters. And the chemistry can range in hardness between Shore A of about 75 and Shore D of 68. This is about the softest version that you will find, and it prints at about a Shore A of 90. So the actual polymer itself, if it would be in a granule form, would be a little softer, but then as it goes through the process, it gets a little harder as it's laser sintered, which gives us the Shore A 90.
Something I'll kind of talk about briefly is that you talked about the processability. Something that's very important to note is that this is based on the PA12 material that we already run. Our printers in San Diego, we're running the Evonik PA12, and the TPA processes quite similarly to the PA12, which is important. Our workflow is not significantly impacted by switching materials. We can still run through the very similar print times, very similar build times. Well, build and print are the same. Finishing is what I meant to say. Cooling is similar. Everything else is really quite similar. So that means it's not a big shock to change materials. It hasn't been a major change to investigate this material and run it.
So a question for, I think both of you. This material is great, but our standard manufacturing plan does not allow budget for rapid prototyping parts. Do you have recommendations for traditional injection molding material we could transition to after successful testing of these parts?
Definitely. Yes. Yeah, that is something we provide, kind of the part of the slide I showed a couple back, that yes, we have Evonik-based materials. We also have other elastomers as well that we work in, and yes, we can recommend based on particular need. So we can early on prototype with this quickly. It sounds like low budget. Go through that quickly. We're used to that equation, and then stepping into injection molding quickly, or compression molding if that ends up being the case, or extrusion, whatever the geometry is.
And yeah. I was going to say, just go on, Rebecca. There's another question.
Oh, no, I was just going to say, yeah. And so this is very close to the Shore D40, because that's typically what we talk about on the injection molding side. And we do have Shore D40 granules that can be used for molding. If you want to prototype in this material and you want the same chemistry, same kind of performance to transition to the injection molding. And I think GoProto can help with the injection molding, and we can get them granules that would be very similar to this material that you would prototype with.
But there's a lot of questions on durometers. So just as a clarification, the printing of the 3D Elastoprint in the MJF printers is 90A, correct?
Correct. Which equates to about 40D.
Yeah.
And again, the durometer is going to depend on, or the feel of it is going to depend on your design.
Yeah. Which obviously, if you're going to go from prototyping right into molding, then you may not have as many possibilities to be making the lattice structure.
That's right.
Yeah, but in general, yes. So yeah, just to go a little deeper into really what we find is the main value of this material, especially when you're comparing it to other elastomers and other thermoplastic elastomers on the market. This is true for injection molding. This is true for the 3D printing. So it's lightweight. You'll hear low density. So don't think, oh, it's got a lot of holes in the part, it's not durable. Think low density, lightweight. So if you have the exact same part printed in TPA versus general TPU, we're usually about 20% lighter, 20% lighter than copolyesters. And I know lightweighting is a big topic right now. So that a lot of people find advantage when it comes to lightweighting their application or lightweighting, sport equipment. So it goes across a lot of industries. Other consistent properties at low temperatures, that's what the polyether helps with. It has excellent impact strength. We've tested it at minus 20 C and minus 40 C, notched IZOD, and I think we have some notch Sharpie data as well, where there's no break. And again, in traditional, this is known for, it's in high-end ski boots, it's in high-end footwear. So it's nice that we're seeing the same properties in our injection molded end uses. We're getting the same in the 3D printing, which also helps that prototyping to end use application. And then the high energy return. I thought it was interesting when I started this project. I didn't know much about the chemistry because it's very specialty. And I thought, okay, what does this really mean? Is it really lightweight? Okay, yeah, I measured it. Okay, notched impact looks good. Energy return, is it really that much better? So I actually went out and I bought shoes based on just my own, just to do, market research, shoes based on TPU, shoes based on EVA, shoes based on this chemistry. And you can feel the high energy return. So high energy return is like, think Super Bowl. It is, you drop something and how far is it going to rebound back to where you are? And this material rebounds a lot better than the other elastomers. And now it feels good that I really believe in this. And I had someone say to me recently, when it comes to energy return, it is just not fair to compare this material to any of the other elastomers because it's just in a different class. So if you have an application that needs energy return, we would highly recommend you look at this chemistry.
Jesse, did you want to show those parts?
Yeah, there are a couple here. There's one other thing, Rebecca. You talked about low temperature, but also high temperature. This material, with elastomer, we tend to use a different. It's not necessarily heat deflection temperature because it's already will deflect so easily because it's elastomer. We use Vicat softening, which is you take a blunt end. The test is take a sample, blunt end, and then warm it up. And then when the blunt end penetrates the material a certain, I think it's a millimeter or so, then you measure that value. And on average, X and Y varies just a little bit from Z, but it ends up being about 109 degrees Celsius, which is 228 degrees Fahrenheit. So high temperature performance is great as well. So then we were talking about energy return, and I've just got a couple of parts here. Again, this lattice that we were talking about, just looking at, like, when I squeeze it, it returns back to nearly net shape. Again, when compared to the other elastomers that have been out in the market in the past, there's just no way they would snap back in that same way over and over. This is like a little stress ball cube that I've had and I've flexed thousands of times. This part also kind of shows it really well. I'll show this again in a second. This is a duct. When I fold it over and then snap back, the camera probably can't even capture it, and you're probably having some internet delay, but the amount of force that this is pushing back is a lot, and it snaps right back, and you see that there's no deformation where I made the crink or the fold over. I mean, that's just an incredible example.
And with the lattice, one other thing we're noticing, we walk through trade shows and I'm picking up samples of all potential competitive materials. And I do believe there's a time and a place for all material. But as I'm looking at my material, I don't know how old this is, probably over a year. And I'm doing the same thing as you, Jesse. I'm crunching it. And it's not breaking these structures. And I take some other materials that are in the same shape. And man, after a couple months, I crunch them and they're breaking. So it seems to be that it is really retaining a lot of those properties, which is also the benefit in this material. We're using no plasticizers. So the plasticizer is not going to leach out. It's not going to evaporate. It's not going to come out at hot temperatures. It's not going to freeze at cold temperatures. It just stays pretty stable.
Important chemistry info. All right, so then we looked at as a service bureau, as a company that's manufacturing parts. I love Evonik, but we are agnostic with both technology, the 3D printing technology, as well as the materials. So we could choose kind of anything. We've looked at all of them and decided really most heavily to invest in the TPA, and the reason is these types of properties that are showing here. If it's very low fatigue, meaning you can bend it over and over and over again, and it's not, as Rebecca mentioned, it's not just going to start to develop cracks and break in the same way as other materials nearly as quickly. High chemical resistance, some of the questions we were talking about that, we'll address that here in a little bit, talk about the chemistry there. It's a soft 90A. Now, when people think about, well, 90 isn't all that soft, it's like a lot of people are looking for 60 or 70 or 50 durometer. We do a lot of cast urethane simulations of those types of durometers. We do a lot of injection molding. With this material, it, as Rebecca said, or is going to say more, you're looking for a balance between printable, good chemistry, good properties, and softness. And at this point, this is about as soft as it can go without compromising some other things like chemical resistance or printability. You know, its ability to not sag as the print bed heats up and the material prints. It needs to stay stable so that you don't end up with a bunch of saggy parts.
Jesse, I'm sorry, just because you said the saggy parts, I think it's important to say, because we've had internal people say this on another product we're developing in another research center, that their new product that's not out yet, they can do a full build. And I said, well, is that a real problem? And it turns out, I think there are a lot of problems with doing a full build with an elastomer, and you can do a full build with this one, and you can unpack it, and you can let it be cool for a week. We've done experiments where we say we want to see how it unpacks from our full build, take a part on the bottom, don't do any depowdering, and send it to somebody to throw in their PowerShot C or whatever they have for tumbling, and it works. So just to that full build, I didn't realize how important that was for some people. There are people that can't do that today.
Yes, that's huge. It's huge for us as a service bureau to be able to unpack cold, so that we can say run it overnight and unpack in the next morning, and then be cycling through the next print. It's real important. So there's some material properties that are important on the fulfillment side for us for workflow and so on, but then they end up coming out in cheaper parts or cheaper part price and so on, as well as then better part properties like high tear strength, high abrasion resistance. There's also great compressive strength, its ability to take the compression and then snap back. You could compress it and let it sit there for days and days or months and then let go, and it's going to snap back to where it was. That's incredibly important in elastomers. So then some of the questions there, what does this enable that wasn't previously possible? It's kind of a hard question to answer because there's so many different things that it can do. Again, as a comprehensive service bureau where we make complete products for clients, we're offering the ability to provide most of the mechanical parts in a bill of materials. So you've got sheet metal parts, you've got machined metal components, you've got some injection molded components. Let's say you've got a clear lens, clear window, and then you have elastomers. And that's always tripped us up in the prototype phase. Like, well, I can get you a printed photopolymer that's going to feel kind of gummy, sort of weird, certainly not be cosmetic, or I can make you cast urethane, which cast urethane is a great process. You make a silicone rubber tool or a master pattern, silicone rubber tool, remove the master pattern, then you have a tool that you can make multiple parts. We can vary the durometer, we can vary the color, we can do overmolding, a lot of really cool things, but it is still in a urethane-based material that who knows what's really going to happen when it gets cold or hot or sits in the sun for 3 weeks while you're doing your testing, or it's going to vary around a lot. So having the ability now to be able to make something that is truly usable, that I can hand to a client and know that you're going to go away and do your testing and your use, and the thing is not going to break, is extremely liberating and brings a lot of value to the market. So there's a lot of ways to answer what it can do that wasn't previously possible. That's there's so much to unlock there. What can you say about chemical and UV resistance? That's important. We have that a little arrow saying high chemical resistance. Rebecca, maybe you can address that a little bit.
Yeah. So as also a manufacturer of PEEK and PA12, I'm like, and some other specialty nylons, like, well, this isn't as high as those. But as Jesse was talking about the balance, so the softer you go, the lower the concentration of PA12 and the lower the chemical resistance is going to be. So we're doing a lot of testing, and of course, it depends on your application. With water, it's fine. Dilute sulfuric acid, it's fine. Sodium hydroxide, it's fine. Some oils, you have some weight gain, and some alcohols, we're going through them because you can have some challenges there. So it really depends on your application. It's not going to be PEEK. It's not going to be PA12, but it sounds like based on some of the options available today, that it does have some different or increased properties for chemical resistance. So we definitely welcome questions. If there's something specific for your application, I believe our contact information is going to be at the end. Feel free to reach out to us and we can see what we can generate for you.
Rebecca, there's one question right now, just to further dive into that area, is fuel, gas, and grease resistance at less than 130 F.
Yeah, we need to do some more in-depth studies because it's one of those borderline because of the softness. So for PA12, we actually, one of our big businesses, we have successfully placed metal fuel line tubing in a lot of the automotive industry. So works in the fueling, it's great. Because it's the soft one, we need to do some more in-depth testing. And then also wanted to, I didn't address the UV resistance. So this particular grade, because we were trying to balance the properties to get something out now, doesn't have additional UV resistance. So the part's not going to fall apart if it's on your windowsill. But again, we're generating those numbers. And if further UV resistance is needed, that's something that we can add value, again, because we have an end user with GoProto, we have HP as a partner. If there's the right business case, we can for sure add additional value to these, whether it's higher durometer, it's the UV resistance, it's skin contact, something like that.
I'll also say, thank you, Rebecca, very much. I'll also say from the product development side, I've been in the low volume space for a long, long time where, say, we've made photopolymer parts that are elastomer, i.e. objet. And that is a photo process where it's exposed to UV light to phase change it from liquid to solid. And when it's done printing, that phase change doesn't stop. If you have it exposed to the lights in your office, like the fluorescent lights above me, or like Rebecca said, sitting in your windowsill, or you're using it, it's going to continue to cure, and it'll go from kind of clear or amberish to full on yellow. Like it starts to look terrible, and then it also kind of crystallizes on the exterior surface. It becomes more brittle. It just continues to change over a very short time. So a part that you may have paid hundreds or thousands of dollars for, depending on its size, will go from being semi-useful to unuseful in a very short time. And this material won't do that in anywhere near the same time. Now that's on the prototype side. The production side, what Rebecca's alluding to is, like, say you're making roof racks, or you're making something that's going to be out on an automobile, on the bumper or so on. This hasn't been around long enough in the 3D printed version for us to really have a lot of case studies that can say, but I know that it will last for, like Rebecca said, at least a couple of months. If it ends up being something that breaks down, it might change a little bit in color, maybe a little bit, and then properties, I don't think are going to be affected in that amount of time either.
But it's also something, if needed, we can look at our next generation product with the UV, with additional UV resistance. That's right. Something that we do with our injection molded grades today. So then again, to go back to prototyping to production, the Shore D40, close to Shore A90 granules we have in heat and light stabilized. So then that's going to offer additional protection versus this grade.
So we got a few more questions on materials, material properties. We need to keep moving on, but I'll throw them out to you guys. Maybe you can answer them real quickly. Sure. First one being, what's the surface feel? Is it sticky or smooth?
Great question. That's actually one of the reasons why we've kind of worked a little bit harder. I've got a TPU part here versus the TPA part. And the surface feel of them, they both kind of have a grainy finish because they're just bead blasted. Kristen, maybe you can switch so I'm not tiny. There we go. So the TPU part feels kind of hard and slippery. The TPA part, the material that we're talking about here, is much grippier. Just its basic finish is grippier. It feels more like what you'd kind of consider an elastomer feel. It doesn't feel crystallized on the surface.
Grippy like rubber, not like photopolymers that I've felt where you're picking up dog hair.
That's right. But then once I talked about vapor smoothing earlier. So again, we can take this part and put it in our vapor smoothing machine, and it reorders the surface molecules. Then it becomes like full on grippy. It feels like what a shoe sole does. When you slide the parts together, they tack, but it's not in a way that it feels like if you leave it there for a little while, it's going to have, I've seen this in prototype parts, like it's going to reshape and then be stuck. It's just like a production.
It feels like rubber. So not sticky
like
photocurable. It feels like rubber.
Exactly. When I put these, go ahead.
I have to tell you, I showed, so I'm, my parents are third generation automotive business, auto parts. And I showed my mom last night some of the parts and she said, this will be huge in automotive. We have parts like that all the time. And she felt it and just thought it was a regular part that they buy.
That's right. Exactly. And so how does it feel? How does it stick? Actually comes into play when you're considering, I showed a duct part as well. When you're considering sealing and so on, once you actually smooth it, unsmooth, it doesn't seal very well. It is grainy. It will wick moisture through it or across the surface because it has high surface energy. Once you smooth it, it's got lower surface energy. It will seal much better. It's still not going to work for like a 40, 50 durometer compression set seal. That's not its space. It's more about, like, say, if you had a hose clamp on here, you expected it to hold up to air or liquid pressure. It's with a seal, it's gonna do great.
Yeah, water and airtight for sure. Yep. Once it's sealed.
Exactly. Okay, so we've got just a little time check. We've got about 13 minutes and a bunch more information to kind of go through. So we talked already about a little bit about the difference between TPA and TPU. We offer both. TPA has shown a little bit better compressive strength, certainly rebound. It's easier to process for us, so it's faster, better parts. TPU still has some applications, of course. It still compresses and is still elastomeric, so there are some times where it works okay, but the TPA in general works a little better. As I mentioned, it vapor smooths really well, so that means that we can improve the elongation. This material has about a 300 to 400% elongation, depending on whether it's in the X and Y or Z and whether it's smooth or not. And this is a little test dog bone that is just an example of how it would perform. Here's another part that I can pull, and so the elongation in that, this is just kind of accordion, but I could just take it and stretch it further like a rubber band. It will continue to stretch. The TPA performs better in that sense. When would I use one over the other? That's going to kind of depend on your application. I've just talked about it. It just kind of depends on the mechanical properties that you're looking for, and one of them is probably going to shine through. And generally, we found overall the TPA performs a little bit better overall. How does this compare to traditional molded elastomers? It's very similar. It's just essentially powdered version. So that's really exciting. It's not like, oh, well, it's a totally different chemistry and everything. It's got some different engineering, let's say, to the elastomer, but it's really very similar to the injection molded version. What are the tolerances on resolution? Tolerances with 3D printing are a big topic, obviously an important one. The answer is that I can't just say, well, it's plus or minus 3 thousandths or 4 thousandths, because it's going to vary on your design. It's going to vary on packing density, vary on the features, and so the answer is that it's going to be kind of dependent on your particular process. We are talking about, on average, being in the 5 to 10 thousandths range somewhere, again, depending on your design. And like that TPA part at the top, it's going to stretch a little bit or kind of deform maybe in printing and finishing. But the print process itself is capable of plus or minus 3 thousandths at least.
Jesse, on a somewhat related topic, what's the minimum thickness of the parts?
Yep. Yeah, great question. Like with most 3D printing, you're going to want to be aware of anything that's less than about 1 millimeter or 40 thousandths. And that is in individual feature size or wall thickness. We can build some incredibly thin parts like this part. Again, I've got a orthotic shoe part that is about 1 millimeter thick, and it prints just fine. It also can be folded over and crunched, and it pops, right back. And that is about 1 millimeter thick. It's incredibly capable. So being that this is powder based, we don't have to mechanically remove supports, which often then put stress on the part and break it. Like with stereolithography, it can print thinner walls than multi-jet fusion can, but because you have to mechanically break off the supports, you often end up breaking the part because it's like tissue paper, like a lasagna noodle. It's very uncooked. Very important distinction. So it's because it's powder based, we can essentially just move it out, and you're not going to break the part, especially when it's elastomer and it can flex. So to be thinking about anything that's less than about 1 millimeter. If you have specific questions about it, we can talk about it. A case for elastomer and things that you could use are automotive fasteners and so on, and living hinges are a big thing, and that often gets down into the 20 to 25 or thousandths, or like 0.5 millimeter or so, and it will print those, but we'll need to look at it carefully and analyze it in design for manufacturability stage.
And then
Okay.
the final question you had was on the surface finish, which you touched on earlier. But one of the questions here as well is when it's vapor finished, is that all the surfaces both inside and out?
That's a good question. It is vapor, so it will tend to go toward, inside a part. So like lattices that are difficult to reach, you couldn't mechanically get in there and polish them. It will get in there and reach. It is, it's not forced by tubing. It basically flows into the chamber where the part sits, and it will flow where it flows. There's a fan in there, but it doesn't go directed. So sometimes it has a hard time reaching deep inside of a cavity. But most of the time, it will get in and reach difficult to reach places.
And while we're looking at this picture, I was just going to say there's one other question. Does it come in different colors?
Good question. At this point, no. At this point, it is gray, unfinished, and it's black. Once we actually dye it with RIT dye and then vapor polish it, and so it's gray or black. We're working on that. There will be a different answer in the near term, but right now it is gray or black.
And let me just say, the material virgin is white. We're not the hang up.
Yes, the reason it's black is because, or gray, is because the fusing and detailing agents, it's a thermal process, so you need a dark color to be able to absorb that UV light and the heat that sinters the nylon together. Or the nylon-based material. That's why it ends up a dark color.
Yeah. The one thing I saw in your question about the seal, and I know you talked about it earlier, I don't know suitability for production seals, but this is one area we looked at in our initial investigation. And we made some prototype parts for people, including one that was gigantic. And we actually, it was printed in a little ball, like you mentioned earlier. You can bend your part. And it worked. It was equipment for spraying paint. And as a prototype, it absolutely works. So for sure, it would be good to look at for sealing for prototyping, because I understand that can be an expensive process. I just don't know that it could then 3D printing it be used in the production. But for sure, I think it should be looked at for sealing, for prototyping seals and prototyping new equipment and design.
Yep. Also, once smooth, if you drip water on it, it will bead right off. And water and other liquids as well. Kristen, you were going to say?
So Jesse, yeah, I think because of time, so we have these reference designs. I think maybe, so we can get to some, there's quite a few questions still to get to as well. Maybe we can skip ahead to the last slide. The reference designs are on GoProto's website. So you can, the slides we're going to skip, you can actually see there are those details on the website.
We've shown a lot of parts during the course of this as well. So hopefully you've seen that they're great references.
And there was also a question about sharing the presentation. This presentation is being recorded and will be put up also on GoProto's resources page, so the resources page has both the present and past webinars, as well as those reference designs that I mentioned earlier.
And we'll email each of you that have attended, and those even that didn't here with, in case you missed us, here's a link to the presentation, or to our website where the presentation lives. So we'll send that to you. Okay, so then this slide just kind of shows just some of the general targets. We've focused on, again, our company and Evonik too, we are targeting many different industries. We look at industrial products. Medical is a big part of it, which it doesn't show on this particular slide, but medical is a big part of our focus. Sports equipment is a huge focus with this, and then automotive. And those are some of the reference designs that we were going to be talking about. And some of the things that can be done with this that couldn't be done before are things like usable, let's talk about industrial or automotive both, usable HVAC ducting, usable fasteners, usable say harnessing. I think we say that in the automotive. Harnessing is a big thing. I showed this this part earlier. Right now I'm small again, but you've got parts that can't be really made in prototype really any other way until this point, and now you have a material that's capable of doing things that weren't done before. So the applications are huge. Again, we're focusing on industrial products, which includes, say, robotics. End of arm tooling is big for us. Things that are grippers and things that, say, have variable compression so that you can get just the right grip without damaging whatever it is that you're holding on to. But someone asked earlier, is it grippy? Like, so to know that you can compress and grab, but then it's grippy to rely on some friction or to do something during the, with robotics. That's a huge capability of this. And it's going to stay consistent over the days, months, years that you might have it in that robot or on that product is incredibly important. It's not going to become brittle over time. Nowhere near like the other 3D printing materials. Non-pneumatic tires is important for industrials and automotive. Electronic covers I talked about. We've got a great little electronic cover here that's some nice material example. Sports equipment, Rebecca mentioned lightweight. That's important because obviously sports equipment, something you're going to be wearing, helmets, goggles. Winter sports, it has that cold weather impact resistance capability. Lightweight is really important. So it's you can make parts that are incredibly light that may have been heavier in other materials or heavier because of other manufacturing processes. Say you've always known about lattices but couldn't use them because you couldn't manufacture it in injection molding. Now you can 3D print it in a usable material that you can make lots and lots of parts with. So great application there. And then automotive, that's important to know. Things like we can 3D print. I want to just briefly mention this part. You'll be able to see we can 3D print in texture. So this has got a leather or animal texture on one side. On the other side, we showed off with a bunch of geometric textures with features that can't be injection molded. This kind of bunch of undercuts and so on. So you can actually 3D print in texture that's a usable production grade texture. So the cosmetics can be incredibly production capable. So that's important to know on the automotive side, that often visible interior components, that's important. Okay, I think we kind of ran through a bunch of those. Go ahead, Rebecca.
Yeah, and I see a bunch of questions that would be quick to answer. If we run out of time, can we reach them later, or should we just say?
Yeah, we
like
can definitely. Yeah, we'll reach out
Okay.
to each person individually and talk with them about their individual questions. But Kristen, maybe you can kind of roll through. We've got a few minutes here. We can. You're on mute again, Kristen.
Oh, and I can
one
see
that's
some
really
of
good
them.
that is, I think, really applicable to you guys is, can engineers give a goal feel, quote feel, and have GoProto recommend a lattice structure to achieve this feel? For example, if we plan to use 50A in production, can GoProto mimic this with a 90A material?
Great question. Yes, we can. That's in development because this is a new material, and that idea is newly being developed. It's going to be kind of a let's work together and get it figured out. But yes, we're actually working with N topology. Some of you may have heard, and General Lattice to do exactly that, like material libraries to help with what is FEA, essentially, to be able to take a design and apply some design constraints to help use the computer and the programs to quickly make lattices that end up achieving the same durometer that you're looking for. So yes, we can try that. And also just the ability to, as I mentioned earlier, finding the Goldilocks, printing several different versions in one print quickly and inexpensively can allow you to test a bunch of different versions at once for low cost.
Great. Well, we do have a lot of questions here. As Jesse mentioned, we will reach out to you individually. If you've submitted a question here and we haven't answered it, we will get back to you. You can also email at quotes@goproto.com if you have any additional questions as well. And Jesse, Rebecca, thanks. Thank you both for participating. Any closing words?
No, I just wanted to thank you very much, Kristen, for helping organize. Rebecca, it was great to talk to you as always. Great to talk with the users. Hopefully, everyone feels like this was an interactive, good chance to answer questions. That's what we're here for. We're not just here to sell you a material or parts. We want to help you develop your product, and happy to talk with you about that going forward. And we can work closely, with HP, for example, and Evonik about your specific application. We can help you, like you need to qualify the material, you need to get it in, you need to know more about the chemistry so that you can get it into a production application. We can bring in some serious horsepower to help you investigate this material, print parts, get them in, try them, test them, make sure they're going to work for your application. So we're set up and ready to roll.
Yeah, and I saw someone just asked about email. So I don't know if we have that, or can we send out email for questions, I guess, to the people that asked for email?
We'll email out to every registrant, both people that attended and the people that didn't, and we'll have our contact information in there.
Okay,
and
perfect.
Rebecca, we can include yours too.
All right, great. Well, and thank you, Jesse. Thank you for involving me. It's really exciting for us. It's not that we're making parts, but to be able to support you making parts and move the industry forward is really exciting for us.
Completely agreed. All right, thank you, everybody.